Hi guys, hope you're having a great day. Today we're going to look at 1.7, which is rational functions. So the good news about this section is that you've seen so much of this before. You did a whole unit on it in Math 3. The bad news is that it's just a lot of information. There's a lot of stuff going on between holes and x-intercepts and y-intercepts and different types of asymptotes. So we will kind of go through and review all this. But again, good news is hopefully it's a little bit of review. All right, so rational functions. When we divide like a polynomial by a polynomial, it creates what we call a rational function. Think rational is like a ratio, which is a fraction. So the domain, the first thing we're talking about is the domain is restricted because we know that we cannot divide by 0. So the denominator cannot equal 0. So I'm just going to write this as n of x, which is my numerator, over d of x. And we know again that this denominator cannot equal 0. So when we're asked to find the domain of a function, we'll talk about kind of in a few minutes of what this means. But the first thing that we want to do is factor this. So this is going to be x minus 6, x minus 2. And I know that that denominator cannot equal 0. So for example, in this case, if I set that equal to 0, I get x equals 6 and x equals 2. So those are the two things that x cannot equal. We'll talk about in a minute that those are actually vertical asymptotes, but for now we just know that they're restricted from your domain. So we want to go from negative infinity to positive infinity, but we don't want to include 2 or 6, because if it equals 2 or 6, then my denominator equals 0, and I can't divide by 0. So that's going to look like negative infinity. I'm coming from negative infinity. It's all good. I have to stop at 2. I use a parentheses because that's not included. 2 to 6, stop again at 6, and then 6 to infinity. Okay, so just make sure you're familiar with that notation. All right, so this is kind of, you'll see some of this when we talk about limit notation and end behavior, but one new thing to kind of add is if I say x approaches a, which a is some number, so it could be like x approaches 4, and then a little minus in the kind of like looks like an exponent, that means from the left side, okay? And I'll give you an example of that in a minute. This means from the right side. Okay, so if I'm moving at it from the right side, again, we'll look at an example of that. You're familiar with it approaching infinity or negative infinity as far as x, and then as far as what does that function actually approach. Okay, so let's look at an example of this. So in this example right here, okay, first of all, we have vertical asymptotes. Now I'm just going to go ahead and sketch. It looks like, and usually you do vertical asymptotes with a dashed or a dotted line. It looks like that this vertical asymptote is at x equals negative 3. Vertical asymptotes will always be in the form of x equals. I'm just going to write it as x equals a. We know in this example it's x equals negative 3. So we can analyze this, okay? X approaches a, which is my vertical asymptote, from the left side. So I'm going to do it in context of this problem to make it a little bit more applicable. So when I'm coming at this vertical asymptote from the left side, I see that this is going up. So if this right here, if I said the limit as x approaches negative 3 from the left, that would be positive infinity. It goes up. If I'm coming at it from the right side, I see that that goes down. So the limit as x approaches negative 3 from the right equals negative infinity. And something that tells me that this is a vertical asymptote is that those are, one is going to positive infinity, one's going to negative. If there was a hole right here, then both the left and the right side would approach 1, for example. All right, so then horizontal asymptotes are in the form of y, let me get a different color, equals b, y equals some number. So in this case, it looks like maybe it's at y equals 2, okay? And so as we go to negative infinity or positive infinity in terms of our end behavior, it will approach that horizontal asymptote. So in this example, as x approaches negative infinity, as it goes to the left, it's getting closer to 2. And as it goes to the right, it's getting closer to 2 as well. Okay. So there's 3 cases when we're talking about finding horizontal asymptotes that you learned back in Math 3. Case number 1, we're always looking at the degree. Remember, the degree is the highest exponent. So if the degree of the numerator is less than the degree of the denominator, think like 5x over 3x squared. This is degree 1, this is degree 2. Then the line y equals 0, it's bottom heavy. It'll always have y equals 0 as the horizontal asymptote. If they're equal, think 3x squared over 5x squared, okay? Then the ratio of the leading coefficients is the horizontal asymptote. So in this case, it would be y equals 3/5. And finally, if it's bigger on the top, so think 3x squared over 5x, degree of 2 on the top, degree of 1 on the bottom, it has no horizontal asymptote. So let's look at just a couple examples here. In part A, the degree in the numerator is 0 because there's no x's. The degree in the denominator is 2. Okay, so this would have a horizontal asymptote at y equals 0. It's bottom heavy. In B, the degree on the top is 1, degree on the bottom is 1, so I divide the leading coefficients. Leading coefficient on the bottom is 1. 3 divided by 1 is 3. And then for part C, the degree on the top is 2, degree on the bottom is 1, so there's no HA, no horizontal asymptote. All right, so if we have a case like C, where there's no horizontal asymptote, it's possible that there's something called a slant or oblique asymptote, okay? So all that'll look like is it'll be a linear equation, okay? And just like what you think, it slants, okay? Because it's a linear function. It might be something like y equals x minus 2, for example. And this only occurs when the numerator is 1 degree of the numerator is 1 degree higher than that of the denominator. So this one would have a slant asymptote. If I had something like 3x cubed over x, that's 2 degrees higher, so that would not have a slant asymptote. To find the slant asymptote, we're just going to go back to polynomials, and we're going to do polynomial division. I'm going to do synthetic division just because it's faster. So if I'm dividing by x plus 5, negative 5 goes in my box. And then I have 1, negative 6, and 7, my coefficients. Bring it down. 1 times negative 5 is negative 5. Add down negative 11, 55. And then when I add that, I get 62. Now, for the slant asymptote, the remainder doesn't make a difference. So this is the number, this is the x. So y equals x minus 11 would be your slant asymptote. So not too bad. And again, if you were needing to graph that, it would just be a line, okay? Slope of 1, y-intercept of negative 11. All right, so some other things you may want to find are zeros, vertical asymptotes, and holes. Okay, so the first thing you're going to do is simplify the rational function by factoring. Okay, find the zeros of the numerator and the denominator. If the 0 is common, meaning if I have x minus 3 and x minus 3, you have a hole. Hole is what you cancel out. If a 0 is just in the denominator, you have a vertical asymptote. And then if it's unique to the numerator, you have an x-intercept or a root or a 0. Okay, so let's go ahead and let's take a look at an example of this where we kind of find all of those things. Remember, the first thing we want to do is factor this first. I see there's a GCF, which is x. I see there's a GCF on the bottom, which is 3x. So that is going to be my very first step. Okay. Next, what I like to do is cancel out any common factors because I know that'll create a hole. I see an x and an x. Remember, you cannot cancel these x's because they are grouped with that minus 3 and minus 2. So that means I have a hole at x equals 0 because it's just x. If it was x minus 3, the hole would be at x equals positive 3. So to simplify this, it would just look like this. Okay. Now, if I wanted to find the y coordinate of that hole, I know that x is 0, so I'm just going to plug that in. So I have 0 minus 3 over 3, 0 plus 2. That gives me negative 3 over 3 times 2 is 6, or negative 1/2. So that is your coordinate of your hole. That also means that the limit as x approaches 0 from the left side would be equal to negative 1/2, because think this is kind of what that hole looks like on the graph. So coming at it from the left, it's going to equal that y value, and coming at it from the right. It's also going to equal that y value. All right, so next let's talk about what else does it want? Vertical asymptotes. So vertical asymptotes is when you set your denominator equal to 0 after you factored and canceled. I don't really need this 3. It's not going to affect it. So I'm just going to do x plus 2 equals 0, minus 2 from both sides. X equals negative 2 is your vertical asymptote. Okay. X-intercept, set the numerator equal to 0. It was x minus 3, so that means x equals positive 3. I like x-intercepts and y-intercepts written as ordered pairs. X-intercept means the y value is 0. Now, if I wanted to find the y-intercept, that means the x value is 0. So I can just go ahead and actually, in this case, there's a hole at 0. So there's not going to be that y-intercept there because that was a hole. Okay, it's just going to approach. If I didn't have a hole at 0, though, I would just plug in 0 for all my x's and see what happened. Lastly, just because we've been talking about, let's do horizontal asymptote. You can look at the original or the simplified. I'm just going to look at the original. Degrees are the same. There's a 1 over 3. So the horizontal asymptote would be y equals 1/3. Okay. All right, let's do one or two more examples. Okay, let's look at this one right here. Okay, remember the very first thing you want to do is factor the numerator and the denominator. So if I factor the numerator, -9 on the top, -8 on the bottom, -9 and 1, 3x squared minus 9x plus 1x minus 3, 3x, x minus 3 plus 1, x minus 3. So my factors are 3x plus 1 times x minus 3. Again, that is not how you have to factor, but that is just a way to factor. I factor by grouping. The denominator is the difference of squares. X squared minus 9, so x plus 3x minus 3. I notice here that x minus 3 is a common factor, so that's going to cancel and create a hole in my graph. Okay, so 3x plus 1 over x plus 3 is what it looks like when it's simplified. Coordinates of the hole. Since I crossed out x minus 3, that means the x coordinate of my hole is positive 3. To find the y coordinate, I'm just going to plug that in. 3 times 3 is 9, plus 1 is 10 over 6. I can simplify that to 5/3. Divide top and bottom by 2. Now, when we're talking about domain, we need to restrict the vertical asymptotes where the denominator equals 0, but also don't forget about that x coordinate of the hole. So in this case, the domain cannot equal -3, and it also can't equal +3 because that's where the graph does not exist. So if I'm coming from -infinity, I stop at -3 first. Then I have to stop again at +3 to infinity. When we're talking about the range, the two things we need to exclude are the horizontal asymptotes, because remember that's in the form of y equals blank, and then also the y coordinate of the hole. So first of all, the y coordinate of the hole we know is 5/3, and the horizontal asymptote we haven't found yet, so I'm just actually going to jump down here and find it. The degree of the numerator and the denominator are the same, so I'm going to divide the leading coefficients and I get y equals 3. So that means that y also cannot equal 3. So we got to think about what's bigger here. Okay, so 5/3 is less than 3. So that's going to be the place I have to stop first. Looks like that. And again, we already talked about vertical asymptote, set the denominator equal to 0. That gives me x equals -3. All right, they've already graphed this for you, so we're just going to look at a few limit statements here. The limit as x approaches -infinity. This is just straight up end behavior. We're going to look at what's happening to the left. I see that it's approaching that horizontal asymptote at 3. Same thing for the right side. I see the right side is approaching that horizontal asymptote at 3. All right, then it asks the limit as x approaches -3 from the left side. Okay, so let's look at this graph. -3 we know is the vertical asymptote, and I'm coming at it from the left side. I see that that's going up, so that's going to be +infinity. Now, looking again from the right side, I see that it's going down, so that's going to be -infinity. Lastly, we're talking about as x approaches +3, okay, that is the coordinate of your hole. Notice that the hole is approaching the y value of the hole at both of them. That's the definition of that hole. So we already said the y coordinate of the hole was 5/3. That matches up with what I see there. So it's going to approach 5/3 from the left side and from the right side. Okay, so make sure that you're able to read a graph and read kind of what's going on and what's happening there, so that you can see okay, with end behavior and also the behavior at the asymptotes. All right, let's do one more example. I'm going to go ahead and factor it first. So when I go to factor this, I get 2x minus 1, x minus 3, and then x plus 3x minus 3. So again, this cancels out, so I have a whole at x equals positive 3. To find the y coordinate of the whole, I'm just going to plug that in. 2 times 3 is 6, minus 1 is 5 over 6. So that should be 5/6. Okay, then we have let's do vertical asymptote. What's left in the denominator? X plus 3 is left in the denominator. Set it equal to 0. I get x equals negative 3. Horizontal asymptote, the degree is the same on the top and the bottom. Divide your leading coefficients. Y equals 2. X-intercept, I'm going to set the numerator equal to 0. When I set 2x minus 1 equal to 0 and solve for x, I get 1/2. And then y-intercept, remember our last one didn't have one because there was a hole at 0. Let's go ahead and find this. If I plug in 0 for all my x's, I just get the constant over the constant. So 3 over negative 9, which is negative 1/3. Okay. Now, I'm not going to make you usually sketch kind of by hand, although it's good practice. Where you might see a graph is like on a multiple choice question. So it's really just making sure that you can graph kind of those key points and pick them out and pick out what the asymptotes would look like. Okay. So this kind of, like I said, gives you an overview of the only thing new is maybe this limit notation. I know we did it with end behavior, but like from the left and the right. And then also make sure that you know how to find a slant asymptote. That is important. So again, but a lot of the stuff is stuff that you have seen in Math 3. So just reinforcing some of those skills. All right, so that wraps up 1.7. Have a great rest of your day.